All right, can everybody go ahead and can everybody see my screen okay?
Yep, it's clear.
Excellent. Okay, so today we're going to start a new unit, which is on matrices and systems of equations. All right, so we're going to start with some of the matrix basics. All right, um, and then I'm kind of going to jump a little bit out of order here because I think learning just the basic matrix operations can help out kind of quite a bit, and it's a little bit easier, the basic stuff. So we'll start off a little bit easier today, and then we'll jump into multivariable systems. All right, but today we're just going to talk about how to determine if two matrices are equal, how to add and subtract matrices, how to use scalar multiplication with matrices, how to do matrix multiplication. All right, and so that'll primarily be what we get through today. All right, so first, a matrix can be represented several different ways. All right, first, we can just call it by an uppercase letter. Right. Typically, we start at the beginning of the alphabet, A, B, C. All right, but you don't have to. It can really be anything. All right. You can also denote it by a representative element closed in brackets. Right, and you can see that there where it says inside of brackets there, A sub ij, B sub ij, or C sub ij. Basically, that's just A sub ij would be, any element in matrix A. B sub ij would be any element in matrix B, and so on. Right. But what a matrix really is, and what we need to think of a matrix as, is this rectangular array of numbers, right? So we have in brackets, and it can be as big or as small as you want, all right? But we're going to have all of these different elements in here, all right? Now this looks a lot more complicated than what it really is, right? A sub 1, 1 would just be some number, like 5 or -3 or 10, okay? But what this represents, right, like A sub 1, 1, since we're using A's, then this obviously would be matrix A, like capital matrix A would equal this whole big matrix. All right, so the subscript numbers here, all right, really just represent, it's not 11, okay, it's actually 1, 1, or it's not 32, it's actually 3, 2. All right, the first number tells you what row you're in, and the second number tells you what column you're in, right? So rows obviously go across. So here's row 1, and row 2, and row 3, right? So on and so forth, all the way down to, we'll call this the nth row, row M, right? Because we don't know how many it is, so just some generic letter will suffice, right? The second number, so like 1, 2, 3, any of these, that tells you what column you're in. And columns go vertically, up and down, right? So this is column 1, column 2, column 3, right? All the way over to the nth column, or column N, all right? So for example, A sub 3, 2, all this means is the element that is in the 1, 2, third row and the 1, 2, second column. Okay, that's all that means. So don't worry about it too much. Okay, so two matrices, A and B, are equal when they have the same dimension, which we will say m by n. All right, the dimension is the size of the matrix, and we always say rows first by columns second. All right, so in this case, m rows by n columns. All right, and all of their corresponding entries are equal. So they have to be the same dimension or the same size. All right, and their corresponding entries have to be equal, which means whatever element is in the second row, third column of the first matrix, if the matrices are equal, that same number must be in the second row, third column of the second matrix. Okay, so solve for A11, A12, A21, and A22 in the following matrix equation. Okay, so um, like we said earlier, in order for two matrices to be equal, they have to be of the same size, right? Well, this is a one, this has 2 rows and 2 columns. So we would say that this is a 2 by 2 matrix, right? This matrix also has 2 rows and 2 columns. So this is also a 2 by 2 matrix. All right, so since they're the same size, they can be equal, and we are told they are because of this equal sign here. All right, so in order for two matrices to be equal, their corresponding entries must be equal. So this is the element in the first row, first column, so it must be equal to the element in the first row, first column of the second matrix. So we can simply say A11 is equal to 2. All right. Similarly, right, the element that is in the first row, second column of the first matrix must match with the element that is in the first row, second column of the second matrix. So there I can say, okay, well, A12 has to equal -1. Right, and this kind of works with all of them. So this must match here. So we know that A21 has to equal -3, right? And this must match here. So A22 must equal 0, right? And that's it. That's all there is. Pretty basic and straightforward. So that's what they mean when they say corresponding entries. Right, now we'll talk about matrix addition and scalar multiplication. All right, we'll talk about matrix addition first. All right, you can add two matrices of the same dimension, so you can only add matrices that are the same size. All right, and you can do that by adding their corresponding entries. All right, so this is the very mathematically technical definition of matrix addition. All right, it is not that difficult. Right, it's really if you just this piece up here, right, you can add two matrices by adding their corresponding entries. That's really all you need to think about. Right? This is the important part. This is the technically mathematical definition. All right. However, it is important to note this, right? The sum of two matrices of different dimensions is undefined, right? So if you're ever asked to add a 5 by 7 matrix with a 4 by 6 matrix, you can't. You just say that it's undefined. So let's look at a couple of examples here. All right. So it asks us to add these two matrices. Okay. Well, this is a 2 by 2 matrix because it has 2 rows and 2 columns. All right. This is also a 2 by 2 matrix because again, 2 rows and 2 columns. All right. So since they're the same dimensions, we can go ahead and add these. All right. And all we have to do is add the corresponding entries. All right, so I'm going to add the element in the first row, first column of my first matrix to the element in the first row, first column in my second matrix. So -1 plus 1 is 0. All right, next I can do the element in my first row, second column of the first matrix, add that with the first row, second column element of the second matrix. 2 plus 3 is 5. So we get 5. Right? And I can just do that with every entry. So these two will be added. 0 plus -1 is -1. And 1 plus 2 is 3. And that is our sum. Right? So very straightforward. It's very intuitive. It's exactly how you would think that you should add matrices. All right. So we can do the same thing here. All right. This is a has 1, 2, 3 rows in only one column. So this is 3 by 1. Same 1, 2, 3 here, and one column here. So 3 by 1, 3 by 1, they are the same. So we can go ahead and add these. So 1 and negative 1 will be 0. Negative 3 plus 3 will be 0. And 2 plus 2 is 4. Done. All right. Next example here. Here we have 1, 2 rows. And we have 1, 2, 3 columns. Here we have 1, 2 rows. And here we have 1, 2 columns. So my first matrix is a 2 by 3 matrix. My second matrix is a 2 by 2 matrix. Right? These do not have the same dimensions, so we cannot add them. We simply say that this is undefined. Right, now we'll talk about scalar multiplication. Right? A scalar is simply a number. Right, whenever you hear scalar, and we talked about scalars when we did vectors as well, right? And we did scalar multiplication with vectors. So it's the same thing. It's just a number that we multiply it by. All right, and to multiply, do scalar multiplication on a matrix, all we have to do, what this means down here, is if I take some number and multiply it by my matrix, all I have to do is take that number and multiply it by every single every single element in my matrix. Right? That's it. That's all I have to do. So again, very basic, straightforward, and intuitive. It's kind of exactly how we think it should be. All right, so here it says for the following matrix, find 3a. So 3 is my scalar, right? It's just my number that I'm multiplying. And it gives me this matrix A, which is a 3 by 3 matrix. So to find matrix 3A, all I do is take every single one of these elements and multiply them by 3. So 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. And that's it. Right? So again, very intuitive. It's kind of exactly how you would think it should work. All right, so now we can kind of combine matrix addition and or subtraction and scalar multiplication. So it says find 3a minus b. All right, well, 3a, this is the exact same 3a that we just found in the last example. So 6, 6, 12, negative 9, 0, negative 3, and 6, 3, 6. And then I'm subtracting b, so I'm just subtracting this whole thing here. All right, so when I do that, 3a minus b. All right, well, all I have to do is 6 minus 2, which is 4, 6 minus 0, which is 6, 12 minus 0, which is 12, negative 9 minus 1 is negative 10, 0 minus negative 4 is 4, negative 3 minus 3 is negative 6, 6 minus negative 1 is 7, 3 minus 3 is 0, and 6 minus 2 is 4. And that's it. All right, so not a whole lot different than doing them one at a time. Just takes a couple of steps. All right, so here's some properties of matrix addition and scalar multiplication. It says let A, B, and C, there should be B, M by N matrices, and let C and D be scalars. Again, scalars are just numbers, right? So it says, okay, well, if you take matrix A plus matrix B, that's the same thing as matrix B plus matrix A. Right, that's simply our communicative property. Commutative, sorry. Commutative, which just means order doesn't matter. All right, here we have three different matrices, and it says, okay, if you're going to add them all together, it doesn't matter which ones you add first, right? It doesn't matter if you add B and C first and then A, or it doesn't matter if you add A and B first and then C. It doesn't matter. All right, that is the associative property of matrix addition. All right, here it's it's still the associative property. All right, of course now we're dealing with scalar multiplication, and it says, okay, if I have two scalars in a matrix and I'm multiplying them all together, it doesn't matter whether whether I multiply the scalars together first and then multiply it by the matrix, or if I take one of the scalars, multiply it by the matrix first, and then multiply it by the other scalar. Order doesn't matter there with multiple pieces, so again, that's the associative property of scalar multiplication. All right, here, 1 times any matrix A is equal to itself. All right, that's just called the multiplicative identity property. All right, and here it says, okay, well, if you take some matrix and add nothing to it, then you're left with that same matrix. All right, that is called the additive identity. All right, here if we have some scalar C and we're multiplying it by the sum of two matrices, right, then it says that's the same as multiplying both matrices by the scalar and then adding them. Right? That's just our distribution or distributive property. All right, and similar, same thing here. This is the distributive property, but now we have two scalars in one matrix instead of two matrices in one scalar. So it works both ways. Really, it's not super important that you know these properties. They're all kind of just properties that we've used many times before. And a lot of times it's just easier to use your standard order of operations, right? So here, right, there's two different ways you could do this. You could go ahead and distribute your scalar to both matrices and then add them together, but I prefer to just use order of operations and say, okay, well, let's just go ahead and add what's inside the parentheses first. So -2 plus 4 is 2, 0 plus -2 is -2, 4 plus 3 is 7, 1 plus 7 is 8, and I'm multiplying all of that by 3. So I'm going to get 6, -6, 21, 24, and we are done. Right, we can actually do kind of basic matrix equations, right? So this isn't just some regular lowercase x like we're used to. This is a capital X, so that represents a matrix. So this is some matrix. All right, that's perfectly fine. All right, so we can go ahead and do this. We can say, okay, well, 2 times matrix X minus 2 times matrix A. If we go ahead and do that, we're going to get 0, 6, 4, 0, -8, -2. All right, and that is going to equal this whole thing here. -4, -8, -2, 0, 14, -6. Okay, now I do want you to kind of make note that here I did 2x minus 2a, right? I just multiplied a by 2. You could have also said 2x plus and then multiplied this whole thing by -2, right? Either way, you're going to get to the same point. All right, so like with any equation, all right, we want to isolate the x. All right, so the first thing I'm going to have to do is get rid of this matrix here. So I'm going to add it to both sides. Instead of writing all of that again. All right, so when we do that, we're going to now have 2x is equal to, all right, so negative 4 plus 0 is negative 4. Negative 8 plus 6 is negative 2. Negative 2 plus 4 is 2. 0 plus 0 is 0. 14 plus negative 8 is 6. And negative 6 plus negative 2 is negative 8. All right. Well, we didn't have a definition for matrix division, so technically we can't just divide everything by 2. All right, but really it's the same thing as a scalar multiple of just multiplying it by 1/2. All right, so now my 1/2 and my 2 will cancel, and I will get matrix X is equal to, I multiply every element in here by 1/2, and we get negative 2, negative 1, 1, 0, 3, and negative 4. And that is it. Right? We just solved that matrix equation. All right, so now we're going to talk about actual matrix multiplication. All right, so not multiplication, not scalar multiplication, not where we're just multiplying a whole matrix by a number, but where we are actually multiplying two matrices together. All right, there's a couple of important things here that we need to note. All right, matrix multiplication is not near as intuitive, all right, as scalar multiplication or matrix addition or subtraction. Right, those just kind of make sense. It's kind of what you would think that you should do. All right, matrix multiplication isn't quite that nice. All right, so if we have some matrix A, all right, that is an m by n matrix, so remember rows by columns, and we have some matrix B that is an n by p matrix, then the product of AB is an m by p matrix given by the following. Okay, so that's very important. One thing to note is that the columns of my first matrix must equal the rows of my second matrix. Right? If those are not equal to each other, then we cannot multiply them. All right, and then our answer, our product, is going to have the same number of rows as my first matrix and the same number of columns as my second matrix. All right. So before you even do any multiplication, you should know the size of your product, the answer, the dimensions. All right. And if AB is equal to some matrix C, all right, then you can find any element in C. All right. Now this looks really complicated and kind of can be. All right. So I don't want you to worry about that a whole lot. All right. What's kind of important here is that this is simply row by column multiplication. All right, so we will multiply corresponding elements in the row of the first matrix by the column of the second matrix, and then we'll add them all together. And once you see it, it's a lot easier than what this definition makes it out to be. Okay, so let's look at an example. All right, so this matrix here, my matrix A, is a 3 by 2 matrix, right? Because I have 1, 2, 3 rows and 1, 2 columns. Right, my matrix B is a 2 by 2 matrix because I have 1, 2 rows and 1, 2 columns. All right, we need to check that the columns from my first matrix and the rows from my second matrix are equal to each other. They are equal to each other, so we are allowed to multiply them. All right, and our answer is going to be the number of rows from the first matrix and the number of columns from the second matrix. So I know that A times B is going to be a 3 by 2 matrix. So it will have 3 rows and 2 columns. All right, so AB, which I will just say is matrix C. All right, we know that it is going to be a 3 by 2. All right, and since I called it matrix C, I can now say, okay, well, this is going to be C11. This is going to be C12. Oops, didn't do that. C21, C22, C31, and C32. Remember, these subscripts here, right, just tell you what row and what column you're in, right? So this says, okay, this is the entry that's in the first row and first column, all right, which is obviously here, right? First row, second column, here. Second row, first column, here, so on and so forth. Okay. Well, now, in order to find C11, all right, I am in the first row. So when I said row by column multiplication, we always take the row from the first matrix, and we always take the column, which it says first column also, we take that from the second. Oops, from the second. Son of a biscuit. All right. So now what we do is we multiply their corresponding entries. So the first entry here times the first entry here. So -1 times -3. And then we add that to the second entry here, which is 3, times the second entry here, which is -4. All right. So C11 is going to be 3 plus -12, which is -9. All right. So AB my C11 is -9, the entry in the first row, first column. And now I can do the same thing with C12, all right, except now C12 says first row. Okay, well, I'm still looking at the first row from my first matrix here, but now I want the second column. And remember, column always comes from the second matrix. Make this easier on myself in the future. So now I want the second column. All right, so I do the same thing. I take my first entry here, which is -1. I multiply that by my first entry here, which is 2. I add that to my next entry here, which is 3, times my next entry here, which is 1. All right, so -2 plus 3 is 1. So my first row, second entry, or first row, second column entry is 1. And I just keep doing this, right? So now I'll look for C21. All right, well, now that means second row. So I take my second row from my first matrix and first column. So I come over here, first column, right? And I do the same thing. So now I'll have 4 times -3 plus -2 times -4. All right, so that's -12 plus 8 is -4. So second row, first column is -4. And I just keep doing this. So now I have second row still, but now I want second column. So I go ahead and do that, and I get 4 times 2 plus -2 times 1, which is 8 plus -2, which is 6. All right, C31. All right, so now I am in the third row and first column, and I do the same process. So I have 5 times -3 plus 0 times negative 4. All right, well, negative 15 plus 0 is negative 15. So negative 15 and C3, 2. All right, well, now I still want my third row, so I'm good here, but now I want my second column, so I'm over here. All right, so now I have 5 times 2 plus 0 times 1, so 10 plus 0 is 10. And we are done. All right, once you get the hang of this, all right, you're not going to have to write all of this out every time, and it will go much faster for you once you understand the concept. All right, now sometimes you can have more than just these two pieces, right? If we had more rows and more columns, you would end up with having to add a lot more pieces, and we'll get to one like that here in a little bit. All right, but let's go ahead and look at one more example of this. So here, this is a 3 by 2 matrix, and this is a 2 by 2 matrix. All right, these are the same, so I can multiply them, and my answer, my product, will be a 3 by 2. All right, so my AB is going to be a 3 by 2. All right, well, now to get my first entry here, which is going to be in my first row and first column, right, I always take the row from my first matrix, and I always take the column from my second matrix. So here I have negative 1 plus 0, that's just negative 1. All right, well, now here on first row, second column, I do the same concept. So I have 2 plus 28, which is 30. All right, now this entry that I'm looking at here is in the second row, first column. So I go second row, first column. All right, do my same process here. So 2 plus 0 is 2. All right, now this entry here, second row, second column. So now I do here, same process. Negative 4 plus 0 is negative 4. And next entry I'm looking at here is in my third row, first column. So I go third row, first column. I do my same process. 1 plus 0 is 1. And my last entry here is in my third row, second column. So third row, second column. Do my same process. Negative 2 plus 14 is 12. And we're done. All right, so here we just want to look at a couple of situations. All right, we're not really going to go through and do all of the math because it actually gave us the answers. All right, but just a couple of things that we can kind of discuss. So this is a 2 by 3 matrix. This is a 3 by 3 matrix. So yes, these are equal, so we can multiply them. Our answer should be a 2 by 3, which it is. All right, so we look like, we can trust that that's probably correct. All right, now notice here I take some matrix and I multiply it by this, and I get the exact same matrix that I started with. All right, the reason why is because this is called the identity matrix. And we'll define it formally here in a little bit. All right, but basically an identity matrix is when your main diagonal, which means from the top left to the bottom right, is ones, and everything else in your matrix is a 0. All right, and whenever you multiply a matrix by the identity matrix, you get the original matrix. It doesn't change anything. It's just like multiplying a number by 1. Right? Over here, we see that we multiply two matrices and we actually get the identity matrix, right? Well, whenever that occurs, right, we say that these are inverse matrices, all right? And we'll talk about inverses and how to find them and that kind of stuff another day, but just know that if you ever multiply two matrices and you get the identity matrix, all right, then you know that they're inverses. Okay, so now here, all right, we have a lot of stuff and we end up with not very much stuff. Okay, well, this is a 3 by 3 matrix, and this is a 3 by 1 matrix. So since these are equal, we can multiply them. And our answer should be this, which is a 3 by 1, which, hey, that's what we have. So that works out well. That's quite okay. All right. Well, here, all right, it says, okay, well, what is this thing? Well, this matrix here is a 3 by 2 matrix. This matrix here is a 3 by 4 matrix. Well, we need to check these two numbers here. Since they are not equal, we cannot multiply these two matrices, and therefore that's just undefined. So just a couple of scenarios that you might see. Okay, so let's go ahead and do some matrix multiplication here. All right, so here we get that this is a 1 by 3, right, because I have one row and 1, 2, 3 columns. Here I have a 3 by 1 because I have 1, 2, 3 rows and just one column. All right, well, these things are equal, so we can multiply them. And look, our answer here is just going to be a 1 by 1 matrix. All right, well, remember we are doing here, this is obviously, since I only have one entry, it's the entry that is in my first row and first column. All right, so I'm going to take my first row and multiply it by my first column. All right, so C11 we'll call it. It's going to be 1 times 2 plus negative 2 times negative 1 plus negative 3 times 1. All right, so this is going to be 2 plus 2 plus negative 3, which is just 1. So, bam. All right, and that's it. All right, well, here, if you notice, these are the same two matrices, just multiplied in the other order. So this is now a 3 by 1. This is a 1 by 3. Okay, well, these do match, so we can go ahead and multiply them. And it says here that this is going to be a 3 by 3 matrix, which seems really large for the two things that we're multiplying, but that's what it's going to be. All right, so to get my first entry here, my first row, first column, I take first row, first column. Well, there's only one entry in each of them, so 2 times 1 is 2. Here I'm in first row, second column, right? So first row still, son of a biscuit. So here I'm looking for first row, second column. So first row, second column. So 2 times negative 2 is negative 4. Next entry, still first row, but now third column. All right, so 2 times negative 3 is negative 6. And we can just go ahead and do all of these. I'm not going to move these for every little multiplication that we're doing from this point on, but now I'm in my second row, so negative 1 times 1 is negative 1. Negative 1 times negative 2 is 2. Negative 1 times negative 3 is 3. Now I'm in my third row, so I'm looking at my third row here. 1 times 1 is 1. 1 times negative 2 is negative 2. And 1 times negative 3 is negative 3. All right? So obviously, these two matrices are very, very different. All right? So if I take the same two matrices, but multiply them in a different order, and I get something very different, well, what does that show me about matrix multiplication? It shows me that matrix multiplication is not commutative. Probably should have been a second M in there, but whatever. All right, so with matrix multiplication, order does matter, right? So do be mindful of that. Okay, so now we're going to kind of look at how we could use a graphing utility to find the product of A, B, given A and B down there. All right, so what I'm going to do is pull up my calculator here. Okay, so if you kind of look at your calculator keys here carefully, if you look above this x to the negative first button, you'll see here in blue it says matrix. All right, that means if you hit the blue button, the second button, and hit this x to the negative first button, it will take you to the matrix menu. All right, now we want to edit, all right, a matrix. I want to actually put numbers in for it, the numbers that were given to us. So I go ahead and hit enter there. All right, this is a 2 by 3 matrix. So I say 2 by 3. All right, and now I just go ahead and fill in all of these numbers. So 1, 2, 3, 2, -5, and 1. All right, well, I need to do that again for matrix B, so I go ahead and hit the second matrix again. I go ahead and go over to edit, but now I go to matrix B. All right, in matrix B, if we see here, it is a 3 by 3 matrix. So 3 by 3. I go ahead and punch all of these in here. So -3, 2, 1, 4, and -2, -2, 0, 1, 2, 3. All right, so we can go ahead and quit out of here now. All right, if we go back to that matrix menu, all right, well, now I have the matrices that I want in there for matrix A and B. So under my names column here, if I just hit enter on matrix A, it takes me out, it puts A in my main screen. And then if I go back to my matrix menu and go down to B and hit enter, it brings out my B. So this is matrix AB, right? A times B. So we hit enter there, boom, there's our solution. All right, a heck of a lot easier than doing it by hand. Right? Although doing it by hand isn't really that difficult once you get the process down.
Mr. Crouch?
Yes.
You went under second matrix, and then you went under math, I think?
Second matrix? No. Like you go over edit when you want to put numbers in your matrix, but if you just want to pull them out to your main screen, you just do it right under names. Right?
Oh, okay, thank you.
We'll get to some stuff that you do under the math menu a little bit later. We'll get to finding the determinant and there's some other things that we can do here, but so we'll do determinant there. We'll even use this REF and RREF later. But for right now, really all you have to worry about is edit to put the numbers in and the names category to actually pull them out to your main screen.
Okay, thank you.
No problem. Okay, so here if we look at some properties of matrix multiplication, right, again, it's not really super important that you remember these, right? If you just kind of think of order of operations like you normally would, you'll be fine, right? But basically here it says that matrix multiplication is associative, right? Assuming that all of the letters are in the same order, and we can do that. Do remember it's not commutative, right? So A times B does not equal B times A. So we just kind of showed that in a previous slide, so do be mindful there. But it is associative, so if we're not shuffling around the order, it doesn't matter which way we do them. All right, here distributive property still holds both ways. All right, and distributive. Here, this is a kind of a form of the associative property again, right? Except now we have a scalar thrown in there, so it doesn't matter. Again, as long as you keep them in the same order, the matrices, that is, right? A and B, A and B, A and B. It doesn't matter how you multiply the scalar. But again, you don't need to worry about these properties if you just think of, order of operations and doing things how you normally should. So here is that kind of formal definition of the identity matrix that I mentioned earlier. All right. So the m by n matrix that consists of 1 on its main diagonals. So remember, main diagonal is from the upper left to the bottom right, if those are all 1s, and you have 0s everywhere else, right? That's called the identity matrix. All right. Do note here that the identity matrix must be square, right? So which means m and n have to be the same number, right? 1 by 1, 2 by 2, 3 by 3, 4 by 4. Okay, there is no such thing as a 5 by 7 identity matrix because that's rectangular, not square. And do remember that if you multiply any matrix by the identity matrix, that you get that first matrix, all right? It doesn't change it. And if you multiply two matrices and get the identity matrix, then those two matrices that you multiply together are inverses of one another. And we'll go ahead and stop there. This is something that we're going to deal with a little bit later. Like I said earlier, I kind of jumped ahead a little bit, so we'll get to that a little bit later. You don't need to worry about that for right now. That's really all we're going to cover for today. So you do have an assignment on Delta Math that covers all of those matrix operations and that kind of stuff. So if you have any questions, you can go ahead and stick around and ask me. I'll tell you, a quiz on Friday. Yeah, you'll probably have a quiz on Friday. It definitely won't be a test. We won't finish this unit by Friday. But you'll probably have one of those, Delta Math quizzes type of deal. So it won't be anything major. But if you have any questions, then you can stick around and ask. If not, you can go ahead and hop off and get started on your Delta Math.
Oh, and before I leave, Mr. Coach, I wanted to let you know that on the 6th, I have a meeting with my recruiter for debt, so I probably will be absent for like 10 minutes, 15 minutes maybe.
Not a problem.
I can get I'll have a school excuse to make sure, so
yep.
I can turn that into Ms. Tucci.
Yep.
Wanted to let you know.
Sounds good. Thanks, man.
Yeah, thank you. Bye.
See you.